So in this video, the experiment 3, molecular mass determination of naphthalene. I'm symbolizing that with S because naphthalene is going to serve as our solute. From freezing point depression. Freezing point depression is a colligative property. Then we'll be employing camphor as our solvent. Okay, so the solute is going to be naphthalene. It's going to serve as our solute. So we'll be able to determine the molecular mass of naphthalene, which is our solute, molecular mass of naphthalene, which is our solute, by employing camphor to be our solvent. Now, it is important to know what freezing point is in order to see how we can employ freezing point determination to get to know the molecular mass of naphthalene, which is our solute. Now, freezing point determination is a phenomenon that occurs when a solute, we have a solute, this is dissolved in a solvent. So it's a phenomenon that occurs when a solute is dissolved in a solvent, and this solute has to be non-volatile. It has to be non-volatile. Okay, now, and the dissolution of this solute in the solvent, naphthalene in camphor, will cause the freezing point of the solvent to decrease. So there's going to be a freezing point depression, okay, due to the solute dissolved in the solvent. Now, this is a colligative property, like I've said before, and it helps to determine the molecular mass of a non-volatile solute. Naphthalene is a non-volatile solute while being in the solution. This colligative property, as I've mentioned earlier, colligative property. Okay, colligative properties are just it's a physical property of a solution. When you have a solute and solvent, solute plus, when you have a solute plus solvent, you have a solution. So it's a physical property of a solution that depends on the amount of solute. So it depends on the amount of solute particles rather than the specific identity of the solute. So it depends on the solute, in the sense that if we're able to employ freezing point depression, which is a colligative property, it's going to help us to know the solute or the amount of solute. In other words, the molecular mass of the solute, being naphthalene, in the camphor, which is going to serve as our solvent, making up the solution. So colligative property is a physical property of solution that depends on the amount of solute. Now we have other colligative properties. We have the boiling point elevation. Boiling point elevation. Now, boiling point elevation is another colligative property, just as we have freezing point depression, which is another colligative property. Now, boiling point elevation rises when a solute is added to a solvent. We will not be dwelling on this. So we also have vapor pressure lowering. This is another colligative property. Now, this vapor pressure reduces when a solute, for example naphthalene, is added to a solvent. Now, in turn, it lowers the rate of the solvent evaporation, that is vapor pressure. So vapor pressure lowering due to the activity of the solute in the solvent will reduce the rate at which the solvent is evaporating. Now we also have another colligative property, osmotic pressure. Osmotic pressure. So I'm just going to write it that way. Now, osmotic pressure presence. Now, the addition of solute to a solvent tends to prevent the flow. Osmotic pressure has to do with flow from the region of lower concentration to the region of higher concentration through a semi-permeable membrane. So the presence of a solute, a volatile solute in a solvent, tends to lower the rate at which this movement takes place, or the flow of the solvent molecules from the region of lower concentration to higher in the same permeable membrane occurs. So it lowers that rate. So these are just few examples of colligative properties: freezing point depression, boiling point elevation, vapor pressure lowering, and presence of osmotic pressure. So in this experiment, molecular mass determination of naphthalene from freezing point depression of camphor, we will learn how to determine the molecular mass, of course, of the solid. Like I said, naphthalene in the solid, using freezing point depression. Freezing point depression. Okay, colligative property. I think we've explained that. Now, the principle behind the freezing point depression. What is the principle behind freezing point depression? Now, it relies on the principles that when a non-volatile solid, we have a non-volatile solid. So when a non-volatile solid is dissolved in a solvent, okay, it lowers the freezing point of the solvent. So when a non-volatile solid is dissolved in a solvent, the freezing point of the solvent is reduced. And this actually occurs as a result of the solute distorting the crystal structure or the crystal lattice of the solvent, okay, thereby making it more difficult for the solvent molecules to freeze or arrange themselves into a solid structure. So due to the presence of the solute, it distorts the crystal lattice of the solvent, thereby reducing the ability of the solvent molecules to rearrange themselves into a solid structure or a solid crystal lattice. So we know what the freezing point is. Now, as a rule, freezing point of a solution is always lower. So freezing point of a solution is always lower than the freezing point of the pure solvent. So the freezing point of pure solvent is always greater than the freezing point of pure solution. This is very important. You should know that. Now, since we've been able to establish for a fact that freezing point depression is a colligative property, it is essential for you to know that the magnitude of the freezing point depression, let me use this as the symbol for freezing point depression, Tf, okay, is directly proportional to the molality of the solution. Let me symbolize molality with this and subscript O. That means if the freezing point depression is just the difference in temperature, the freezing point temperatures of the solution and that of the solvent, okay? Now, the freezing point depression is directly proportional to the molality of the solution. It means that the freezing point depression is equal to, let's introduce a constant. Now that constant, let's call it Kf, multiplied by molality. Now, this Kf you see here is called the freezing point constant. So Kf is called the freezing point constant, and it is characteristic to any given solvent. So there's always a freezing point constant to any given solvent. So in our case, camphor has a specific freezing point constant. So that is this. Now, if molality is 1, we can say that the freezing point depression will be equal to the freezing point constant. If molality is 1, this will be equal to this, so we can have this. Now let us define what molality is in regards to the experiment and the determination of the molecular mass of naphthalene. using camphor as a solvent. How would you quantify molality? Now, molality of a solution, I said I was going to be designating molality with M subscript O, is given by number or moles of solutes divided by kilogram of solvent. Now, moles of solutes divided by kilogram of solvent. What is our solute? Our solute is naphthalene. In this experiment, what is going to be our solvent? Our solvent is camphor. So the molality of the solution, solute plus solvent, is moles of solute of the naphthalene divided by the kilogram of solvent of the camphor. Now let's define what moles of solute is first. Now moles of solute is equal to weight of solute divided by molecular mass of solute. Okay, now moles of solute is defined as the weight of solute divided by molecular mass of solute. In this case, I'm going to be designating the weight of solute to be Ws divided by the molecular mass of the solute. Remember, our solute is naphthalene. I'm going to designate that with MS, which is weight of solute divided by molecular mass of solute. Having defined this, let us define the kilogram of solvent. The kilogram of solvent is just a conversion factor, is equal to weight of the weight in gram of the solvent, that is weight in gram of solvent, divided by 1000, that is kilogram of solvent. In the same way, I'm going to designate the weight in gram of the solvent, which is camphor, by W SOL, subscript SOL, divided by 1000. Alright, having defined what moles of solute is and kilogram of solvent is, what is going to be our expression for molality of the solution? So what I'm going to do is substitute these parameters into this equation. The moles of solute, substitute it into this equation, and it's going to look like this. Molality will be equal to moles of solute, we had it as weight of solute divided by the molecular mass of the solute, that is the naphthalene. This is moles of solute, divided by, so I have a division sign here, kilogram of solvent. We said that it is the weight of solvent divided by 1000. So we can re-express this to be Ws, weight of solute, divided by molecular mass of solute, times 1000 divided by weight of solvent. So molality will be 1000 multiplied by weight of solute, 1000 multiplied by weight of solute, divided by molecular mass of solute multiplied by weight of solvent. Molecular mass of solute multiplied by weight of solvent. Now, this expression, we are going to substitute it to the first equation we once had. And that equation has to do with the freezing point depression being directly proportional to molality. So earlier we were able to establish for a fact that the freezing point depression is equal to minus Kf, which is the freezing point constant, characteristic of any given solvent, multiplied by molality. So we're going to substitute our expression of molality into this equation. So I'm going to have freezing point depression equals to freezing point constant multiplied by molality. And the expression we had was 1000 weight of solids divided by molecular mass of solids multiplied by the weight of solution. Interested in the molecular mass of the solid. Remember, the experiment is about determining the molecular mass of naphthalene, which is the solid, in a given solvent, which is a camphor. So we're going to make MMS, molecular mass of solid, the subject of the formula. And if you do that correctly, you're going to be having molecular mass of the solid will be equal to minus Kf, okay, multiplied by 1000 weight of solids, okay, divide by, so what are we going to have? This freezing point depression, okay, multiplied by weight of solution. All right, this is going to be the expression we're going to be using in this experiment, in the sense that the constant, the freezing point constant, freezing point depression constant, would be given. All right, then we are going to look for this, and we're going to find this from the experiment. This is the freezing point depression. I'm going to tell you what it means. Then we get to know from the experiment the weight of solution and the weight of solid that was taken. So this is how you get to find the molecular mass of a solid using freezing point determination by employing camphor as a solvent. Now let's define the freezing point depression and then show you how you can get that in your experiment. Now your freezing point depression, which is changing Tf, is equal to T1 minus T2, okay, where T1 equals to freezing point of pure solvent and T2 equals to freezing point of solution. So freezing point of the solution is T2, freezing point of the pure solvent is T1. So the freezing point of the pure solvent is that of the camphor, which is our solvent. Then the freezing point of the solution is that of the naphthalene and camphor. So with this value, once you determine their freezing point using a thermometer, you do the subtraction, substitute to get the molecular mass of the solid, which is naphthalene.